Hello everyone, my name is Hua Gao. I'm a postdoc at Institute for Astronomy, University of Hawaii. It is my pleasure to attend this exciting conference and to present my work in the last couple of years. I will talk about our study of bulge structural properties and bulge dichotomies in the Carnegie-Irvine Galaxy Survey, the CGS survey for short. My main collaborator is Professor Louis Ho, my PhD advisor, and the rest of the CGS team. Without further ado, I will start by introducing the CGS survey. The CGS survey is Southern Sky Survey 600 galaxies, brighter than 12.9 magnitude. They were about 80% of them are disk galaxies. The images were taken in BVRI bands in the Las Campanas Observatory. The median seeing of the images is about 1 arcsecond, so the bulges of the nearby galaxies are very well resolved, as showcased by the two galaxies on the right, where we can see the details of the nuclear rings very well. The field of view of the camera is large enough to enclose the very extended galaxies, and still have enough pixels for robust sky subtraction. The 1 sigma limiting surface brightness is generally fainter than 25 magnitude per arcsecond squared, but it's not important for our study because we are looking at the most high surface brightness structures. Our goal is to perform multi-component decompositions to derive bulge structural parameters and revisit the topic of bulge dichotomies using the sizable sample of accurate measurements of bulge parameters. So there are several caveats in 2D image fitting. Some were introduced by data quality, and the others are related to the assumptions of surface brightness models. In the case of CGS, the data quality is superior, so it should not be the limiting factor for the accuracy of bulge parameter measurements. So we only have to worry about the model assumptions. We know for sure that the galaxies cannot be well described by simple Sussex bulge plus exponential disk models. Other than the major components, nearby disk galaxies show a wide range of secondary morphological features, such as bars, spiral arms, lenses, disks, and ovals. Whether or not these features should be properly modeled needs to be clarified. So we start by selecting 10 representative galaxies from the CGS survey and experiment fitting them with different models. The goal is to answer two questions. Which features are not important for bulge parameter measurements? And if they are ignored, what is the magnitude of uncertainties added to the error budget of bulge parameters? I will use two examples to showcase how we tackle this problem. This is a spiral galaxy NGC 6118. We prepared two sets of models. The first one in the top row has the simplest configuration, a Sussex bulge and a Sussex disk without spiral arms. We add a spiral feature to the disk component of the second model in the bottom row. When comparing bulge to total ratio yielded by the two models, we find that there was only a small fraction of difference. This indicates that spiral arms are not important for the accurate bulge parameter measurements. The variation in B over T is about 10%. This makes sense because spiral arms are simply a mutually distorted disk. It shouldn't impact the bulge in a significant manner. So in the next example, I show that disk break is very important for accurate bulge parameter measurements. The first model is a Sussex bulge plus exponential disk plus a ferrobar. It is clear that the model is inadequate, as we can see dark holes inside the bar radius, which means that the model overestimates the disk flux in the central region of the galaxy and the bulge is underestimated. So the only change in the second model is that we replace the exponential disk with a type 2 disk. Now we observe a much better residual pattern in the second model, and the B over T increases by 50% from the first model to the second model. So we go through the 10 galaxies and find some common patterns. The first conclusion we reach is modeling the spiral arms is not important. Ignoring spiral arms only cause 10% of accuracy in bulge parameters. Features that are in the galaxy outskirts, such as outer rings, outer lenses, outer disk breaks, are not important. Their effects are even smaller than spiral arms. Finally, inner disk breaks, rings, lenses needs to be properly modeled because their impacts on bulge parameters can be very significant, and most importantly, their impacts are unpredictable. So we follow the above guideline to successfully decompose 320 disk galaxies in a CGS sample. So for bulge type classifications, we choose using the common evaluation to classify bulges into classical and pseudobulges, despite a very popular method of using Sursik index equals 2. We do that because of the several following reasons. First, of course, because of the pioneering work by Gadotti 2009 that sets up a very good example to follow. Second, another piece of very important work led by Newman in 2017 showed that the common evaluation is able to produce consistent classifications with those based on multiple criteria, including photometric and kinematic criteria. Third, we find that the bimodal distribution of bulge Sursik index cannot be reproduced in our work. I will show the results in the next slide. Finally, we find that the common evaluation sorts bulges into a physically meaningful sequence in their color magnitude diagrams, and the common evaluation is also robust against the population effects. I will provide more details about these results later. So in the right figure, we illustrate how the common evaluation can classify bulges. We select the pseudobulges as bulges having average effective surface brightness centered in a lower 3 sigma boundary of the common evaluation defined by ellipticals. Pseudobulges show a few stars, and the rest of the bulges are classical bulges. Classical bulges show as open stars. The red squares are elliptical galaxies. So here is the Sursik index distribution in the CGS sample on the right, and the results from Fisher and Rory 2008 on the left for comparison. So apparently our Sursik index show a unimodal distribution, while the Fisher and Rory results show a bimodal distribution. Our Sursik index are also overall smaller than their results. We have a smaller fraction of bulges with a Sursik index larger than 4. This figure is the color magnitude diagrams of the CGS bulges. In different rows, the symbols are color-coded by different bulge parameters. From top to bottom, they are color-coded by bulge-total ratio, Sursik index, and the residual surface brightness relative to the lower 3 sigma boundary of the common evaluation. The left panels show the true data, and the right panels show the smooth version. In order to mitigate the symbol overlapping effects and to help examine the average trend, we show that the middle panels where bulges are color-coded by the Sursik index do not present any meaningful trends at all. The top panels where bulges are color-coded by B over T do show meaningful trends. We can see that more prominent bulges are redder and more luminous. In the bottom panel, bluish symbols are pseudobulges and reddish symbols are classical bulges. They are separated by the common evaluation at around bulge absolute magnitude equals minus 19 in our band. The dashed line in the bottom panel is the average separation line for classical bulges and pseudobulges. Compare with using constant B over T to separate classical and pseudobulges. Using a quantum relation can prevent blue bulges from being classified as classical bulges, therefore ensure the consistency between the bulge stellar population properties and their structural properties. So now that we have more confidence in the bulge types classifications, we should compare the statistical properties of the classical and pseudobulges. We find some interesting results and less interesting results. In consideration of time control, I will only report the interesting part of the results and summarize the less interesting results in the next summary slide. In this figure, we compare the apparent ellipticities of classical and pseudobulges. Apparent ellipticity of ellipticals and disk galaxies are also plotted for comparison. So we find that the distribution of classical bulges is skewed toward lower apparent ellipticities, which is consistent with those of the ellipticals. The pseudobulges show a broad distribution that is consistent with those of the disk galaxies. This implies classical and pseudobulges have different intrinsic flattenings, and they are spheroidal systems and disk systems just like elliptical galaxies and large-scale stellar disks, respectively. This is consistent with our expectation based on their distinct formation path. So this slide presents a summary of the differences we find when comparing classical and pseudobulge properties, and also when comparing our results with previous studies. Because of the multi-component decomposition approach, we are more capable of isolating other components from the bulge. Therefore, we find that our bulges are generally less prominent compared with previous studies. As just shown in the previous slides, classical bulges are spheroidal systems and pseudobulges are mini disk systems. We also measure the frequency of pseudobulges as a function of their host properties and find that less massive, optically blue, and gas-rich late-half spirals have the best chance to host pseudobulges. All of these is consistent with the canonical picture, in which classical bulges are products of phylum processes, such as mergers and coalescence of stellar clumps in the high-Z universe, and the pseudobulges are mini disks slowly formed out of the redistributed disk material. So it shows that we confirm previous studies that common relation is a useful tool in classifying classical and pseudobulges. But there are some concerns about the driving engine of the secular processes that build pseudobulges, because we find some confusing results. First, pseudobulges do not favor bar galaxies as their host, and the bar galaxies do not have more prominent pseudobulges than the unbarred ones. There are many possible explanations that need more effort to distinguish. For example, bar-driven pseudobulge growth could be self-limited, and bar itself may not be a long-lived structure. Other non-axisymmetric structures like ovals and spirals could also play a role in building the pseudobulges, therefore weakening the role of the bars. So many of the above results are not reported in the talk. If the audience is interested in details, please refer to my 2020 paper. Finally, there are some bonus results which I consider thought-provoking. This figure shows the mass-based quantity relation. Basically, we replace the surface brightness with stellar mass surface densities in the original flux-based quantity relation. So in this figure, E means ellipticals, plotted as black squares. CB is classical bulges, classified using the original flux-based quantity relation, plotted as red open circles. PB is the pseudobulges, plotted as blue filled circles, UDB here is ultra-dense bulges defined as upper 3 sigma outlier of the mass-based quantum relation. Plotted as magenta filled circles, the green and green symbols are compact early-type galaxies in the high redshift universe. The first thing to note is that only a small fraction of bulges enter the opposite category when we replace surface brightness with mass surface densities. We also examined the overall statistics of the classical and pseudobulges and found that they barely change when using the mass-based quantum relation to do the classifications. This means that the quantum relation is robust against the population effects. The other interesting to know is the ultra-dense bulges are as compact as the high redshift compact early-type galaxies. They are not necessarily the most concentrated or most luminous members among the classical bulges, but they have the reddest colors at a fixed bulge luminosity. All of these suggest that they are relics of products in the high Z universe, just like NGC 1277, only their ultra-dense bulges are embedded in disks and therefore are more difficult to find. This is not the first time people discover such objects, but they have important implications on bulge classifications. If the ultra-dense bulges are truly primordial bulges, what are the other classical bulges, and why are they more diffuse than the original status? An analogy to the two-phase formation scenario of the ellipticals, the other classical bulges might have been through considerable size evolution. We don't know what physical processes are responsible for such evolution, but secular evolution are one of the possible candidates. If that is the case, then these classical bulges are actual composite bulges. This is already beyond the scope of the quantum relation classification scheme, as it is only able to deal with binary cases. To make quantum relation compatible with such application, we have to further decompose the bulge into subcomponents and then perform the classification. However, as I mentioned before, measuring the whole photometric bulge already involves many countable uncertainties, not to mention to further decompose it. So finally, I showed the summary of what I just discussed. I won't repeat them, so I will just stop here. Thanks for your attention. Feel free to contact me through the email or in a Slack channel if you have any questions or comments. Thanks.